Hello students. This course has been developed to give the learners the educational tools to prepare and take the MRSO certification course. This module will discuss the Mr. Safety Manual, MRI, and how it works. First, magnetic resonance imaging, or MRI, is a way of obtaining detailed images of organs and tissues throughout the body without needing X-rays or ionizing radiation. Instead, MRI uses a powerful magnetic field, radio waves, rapidly changing magnetic fields, and a computer to create images that show whether there is an injury, disease process, or abnormal condition present. For the MRI exam, the patient is placed inside the MR system or scanner, typically a sizable donut-shaped device that is open on both ends. You may wonder what MRI is used for. MRI is the preferred procedure for diagnosing many potential problems or abnormal conditions that may affect different body parts. In general, MRI creates pictures that can show differences between healthy and unhealthy or abnormal tissues. Physicians use MRI to examine the brain, spine, and joints, for example, knee, shoulder, hip, wrist, and ankle, abdomen, pelvic region, breast, blood vessels, heart, and other body parts. Today's session will discuss the MR mechanism and learn about the safety manual and MR technician should provide. Let's get started. Before we can talk about MRI safety manuals, we need to know how MRI works. First, we will learn several physics terms, such as static magnetic field. So, what is a static magnetic field? The static magnetic field in MRI is well known for being a safety risk. Unfortunately, MRI is not feasible without it. Depending on the MRI equipment, the static magnetic field can be generated in various methods. These units have one thing in common: they can generate a powerful magnetic field capable of aligning hydrogen nuclei to their vector. Let's see how we measure a magnetic field. 1. Direction. You may already be aware that the magnetic field has the North Pole and the South Pole. Magnetic flux lines go from the North Pole to the South Pole. These flux lines are hazardous in an MRI setting. Moving force lines are not magnetic flux lines. 2. Measurement units. Instead, they are densities with varying field strengths that go from the North Pole to the South Pole. Magnetic fields can be measured in either Gauss or Tesla units. The magnetic field that moves a compass on Earth is around 0.5 Gauss. 1 Tesla has 10,000 Gauss. That means the magnetic field in a 1.5 Tesla unit is 30,000 times stronger than the magnetic field on Earth, while a 3T unit is 60,000 times stronger. You may wonder how an electrical current is created. Let's find it out. 1. Faraday's law of induction is a key idea to learn in MRI. This term refers to the electrical current created in a conductive substance when exposed to shifting magnetic fields. It also explains the magnetic fields that are created by electrical currents. As we will see, this approach raises concerns in the MRI setting. 2. Lenz's force is another key idea to understand when dealing with the static magnetic field. This one-of-a-kind concept illustrates how non-magnetic, non-ferrous, items might represent a hazard while traveling through a static magnetic field. 3. Lenz's law states that an electrical current is created in a conductive substance as it moves through a magnetic field. When an electrical current is created, a magnetic field is created at a 90 degrees angle to the electrical current. This magnetic field will interact with and repel the static magnetic field. In a minute, we'll talk about safety considerations with this approach. We must first recognize that there are several sorts of magnetism. 1. Firstly, when an object is placed near a magnetic field, it will display magnetism. The Pauli exclusion principle describes this. 2. To comprehend this concept, we must first understand that an atom's nucleus includes one or more protons, and sometimes a neutron, and electrons circle this proton. 3. Each orbit has its shell or distance from the nucleus. These orbits are known as orbitals because they are not exactly circular. 2. When put in a static magnetic field, diamagnetism exhibits a repulsive force. This is because each orbital includes a pair of electrons. A diamagnetic substance is one such as oxygen. Diamagnetic substances include copper, gold, and silver. We will learn two more types of magnetism. First, paramagnetism. 1. When put in a static magnetic field, paramagnetism can be considered a tiny attractive force. This force is so faint that it can only be measured and not seen. When one or more orbitals contain one electron, this form of magnetism is created. 2. Strong paramagnetism decreases with rising temperature due to atomic magnet alignment. The attractive force created is proportional to the material's temperature and the number of orbitals containing one electron. Paramagnetic materials include gadolinium. 3. Magnetic fields were stronger in superparamagnetic materials than in paramagnetic materials. Ferromagnetic materials are described as being highly attracted to static magnetic fields and keeping their magnetic field after leaving the static magnetic field for a length of time. Ferromagnetism is formed differently from diamagnetism or paramagnetism. Ferromagnetic materials have directional field domains that line with the vector of a static magnetic field. As previously stated, there are several types of MRI units. Here we will discuss two types of magnets: permanent magnets and resistive magnets. 1. Let's start with permanent magnets. Each will generate a static magnetic field, but the distinctions are in how they do it. A group of permanent magnetic bricks creates a magnetic field in a permanent MR unit. Each brick has a small magnetic field, which, when combined, is powerful. Typically 0.4 T. This unit produces vertical magnetic fields. These devices' magnetic domains can't be turned off without disassembling the magnet. They're also heavy. Comparatively, these units are affordable. Now, what are resistive magnets? This unit generates a magnetic field using electromagnetism. Electrical current is sent through a coil of wire wrapped around the gantry. Magnetic fields are created, and the current through these wire coils determines the magnetic field's intensity. Because of Ohm's law, resistance in this wire will cause friction and heat. Resistance increases as wire current increases. This implies more heat. These units rarely exceed 0.6 Tesla and can be expensive due to cooling needs. These devices can be turned on and off without harm. This machine generates vertical or horizontal magnetic fields. Finally, the superconducting MR unit is the most prevalent clinical application unit. 1. This MR unit operates on the same principles as the resistive MR unit. As a result, it likewise employs coils of wire with an electrical current running through them to generate electromagnetism. The 4.2 Kelvin cooled wire has no current resistance when an electrical current flows through it. When we reach the required field strength, we can unhook the wire coil from its electrical source. As long as the wire coils are submerged in cryogen, no energy is lost. Superconducting MR units can reach 10 Tesla. Titanium alloy wire coils maximize these high field strengths. The advantage of this MR unit is that it does not use as much electricity as a resistive MR unit and has lower operating expenses. 2. When we look at the magnetic field created by an MR unit, we can see that we have directional magnetism, also known as a vector. This factor is also known as B0, B sub 0. We also know that magnetic flux lines, which define the B0, go from the North Pole to the South Pole. So we can compare flux lines to the layers of an onion. This notion explains why ferrous things are drawn to the MR unit. Suppose we envision the core of the onion as our strong uniform magnetic field and each layer spreading outward as a lesser magnetic pull. Let's look at the illustration of a spatial magnetic gradient field. 1. Changing magnetic fields draw ferrous objects into a magnet, not by dragging. If we place one side of our ferrous item in a stronger magnetic field than the other side, it will be dragged in that direction. If this continues, the ferrous object will be attracted to a region with equal magnetic fields on both sides or crash into the magnet. 2. If we placed a ferrous item at the isocenter entirely immersed in a homogeneous magnetic field on all sides, it would not exhibit any attractive force. Some parameters influencing the translational force exerted on an item include its size, ferrous content, static magnetic field strength, and distance from the magnetic field. 3. The rotating force is another issue linked with the spatial magnetic gradient. The MR unit's magnetic flux lines flow from north to south. Magnetic fields move in a circle. Even if a ferrous object is sideways, it will be drawn to the isocenter. Ferrous objects don't need to travel straight because they follow magnetic flux lines. This term explains rotational force. Ferrous implants produce torque when aligned with a static magnetic field. It is time to address some of the safety issues raised by the static magnetic field. 1. Fringe field. The fringe field is the spatial magnetic gradient that extends beyond the MR unit. This fringe field is responsible for the translational force experienced by ferrous objects. The missile effect occurs when an item is drawn to the MR unit. 2. Magnetic shielding. Magnetic shields reduce missile impact. Passive or active. A steel cage is built around the MRI machine to modify and concentrate the magnetic field. Active magnetic shielding uses wire coils in the opposite direction of the static magnetic field coil. This extra magnetic field will cancel out some static magnetism. This reduces the peripheral field.